to showcase their current transportation work. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note, this session is being recorded and all participants' microphones are muted. If you're joining us online, please send your question through the chat. Or if you're here with us in person, feel free to raise your hand. There will be time at the end of the presentations for questions. Now, I'm very excited to introduce today's speakers. Dr. Shinpei Kato is the founder and CEO of Tier 4, a $400 million venture-backed AV company, and a co-founder and chairman of the AutoWare Foundation. He also works as a project associate professor for the Graduate School of Information Science and Technology at the University of Tokyo. He is an internationally renowned expert in computer science and a pioneer in the evolution of open source software for autonomous driving technology. Shinpei was an associate professor at the Graduate School of Information Science, Nagoya University, from 2012 to 2016, where his team created the world's first open source software for autonomous driving technology, AutoWare. He was also a postdoctoral scholar at Keio University, the University of Tokyo, Carnegie Mellon University, and the University of California. Dr. Rahul Mangharam is a professor of electrical and system engineering at the University of Pennsylvania. He leads XLab for building safe autonomous systems and conducts research at the intersection of formal methods, machine learning, and controls. He's the Penn Director for US DOT $20 million Safety 21 National University Transportation Center, led by Carnegie Mellon University. Rahul received the 2016 US Presidential Early Career Award from President Obama and has won several ACM and IEEE Best Paper Awards. He founded RoboRacer.ai for teaching the foundation of autonomous vehicles across 90+ universities worldwide. Rahul served on the board of directors for the AutoWare Foundation and is the director of the AutoWare Center of Excellence, which spans 28+ universities which use AutoWare on their R&D vehicles. He's also a CMU alum. Please help me welcome Rahul and Shinpei as they share their presentation, Reimagining Intelligent Vehicles, the Art and Technology of Open Source.
So thanks for the introduction. My name is Shinpei Kato. Good afternoon, everyone. So I'm pleasure to be speaking about what we're doing about intelligent vehicles using open source. So I was in CMU until 2012. So I really appreciate my career that I built here for this Professor Rajkumar, and which made the baseline for me to start this project. So briefly introduction, the company is, there was some brief introduction. It's a startup based in Tokyo. Relatively large size of startup in Japan. There are many other big startups in the world, so we try to become more and more mature. So we joined the World Economic Forum, and we can recognize as a unicorn community because we joined in order to advocate for the needs of autonomy for the society, because we need the market in order to do the business. So this was last year Davos, and this year the president of University of Tokyo accompanied with us to advocate the needs for the autonomy. We also do some research with the World Economic Forum. What is the market expectation by 2030, by 2035? Long story short, there will be the market. More than 50% of the vehicles by 2035 will be automated, and 10% of them will be completely fully autonomous. So this means that we can be confident doing autonomous driving as part of the business. Also, the open source software can actually accelerate this deployment. there are some details like by region. And Japan also is becoming a very kind of popular country for autonomous vehicles. So kind of we are recognized as a startup, but we also recognized as a provider for the open source software called AutoWare. You can go to the GitHub, just download, use it even from today. There are many users, many use cases, many countries actually already deployed. Now let me explain what you can do with this open source software without any modification, any single line of code modification. This is some data that we recorded from our experiment in Tokyo. So the AutoWare has a basic set of functions integrated, like localization, perception, planning, control. So it can successfully detect objects and localize the position of the vehicle and predict what will happen, then generate a trajectory, then control the vehicle like steering, accelerate and brake throttles to follow that trajectory. These are basic features coming from years ago. So open source is not cutting edge. Open source is the way we provide basic features, well-known algorithms, which not cutting edge, but is ready for deployment. So that's what I believe open source has value. Now, there are many applications that we can build using this open source software. I can introduce a few examples that we do. So robotaxi may be most well-recognized symbol of autonomous driving. And we deployed this even 4 years ago. So no human drivers inside the vehicle, and we qualified to operate this on the public road. But we didn't want to make a mass production of this vehicle because that's not the goal of our business. The goal of our business is to make car makers or other partners be able to do what we have done before. So open source is the way that allows you to replicate and modify what existing applications can do. So this is Suzuki, and this is Toyota. So we actually provided Tokyo Olympics the micro shuttle bus with some autonomous mobility. Now, I also want to make this software vehicle agnostic, not only taxi, but also the buses. We also just started this public transportation services in Japan. Again, no human drivers in driver's seat. So we qualified through Ministry of Transportation and police agency, and a lot of stakeholders now agree on the setup of the vehicle so that it can go for the real business. So certification or certifying vehicles is kind of challenge even today. I only see only a few companies, even in the US, like Waymo, driving a real, driverless services. So it's not only about technology, but also about how we can communicate with the stakeholders. Stepping forward, we started working with Isuzu, our shareholder, so providing the large bus production. And right now, public transportation in Japan is very popular. So we try to replace such a route that is struggling with the shortage of bus drivers. For this operation, we are not yet qualified to operate driverless services, but it will happen within a year. And autonomous driving actually means a lot, not only for public road services, but also this is geofence area, factory automation. We have joint venture with Yamaha Motors. They also shareholder of our company. This is in commercial. So 24 was the 365 days operations already, and more than 100 factories are using our vehicles. Small robots, this is what also we're doing with Rahul Racing. So autonomous driving, the first priority definitely is the mobility services, but it's also useful for new entertainment. And now I'm very excited about providing superhuman function. Maybe in the future, I think we can provide fastest lap than a human being. So there are only limited case studies, use cases. So open source is infinite. Like everybody can basically implement their own application. So to support these users, we like to develop environment which is easy to use. The field testing sometimes difficult because you always put yourself on risk of accident. So I'm interested in providing the world simulator, which exactly imitation of the real world. Left top, it's a digital twin, it's an imitation of the real world. And left bottom, it's just a global map. And now right-hand side, right top is the result of software. If you know robotics, we use ROS. So ROS has the viewer and some system. So this system does not recognize, this is fake. The system believes that this is a real world because texture and digital twin looks really the same as what the real world is happening. Now we want to also improving this simulator using generative AI. So building a digital twin today is a little bit expensive, taking some under complex, things. So instead, we like to just use the videos from vehicles and use the generative AI to generate the real world that can actually predict what will happen. So left-hand side is the real data. The right-hand side is the prediction from the generative AI. So you can see that the prediction and the real data almost match, means that the generative AI can successfully predict what will happen. If we can do this, then we can leverage this, this system for the simulation to test not in the real world, but also in, yes.
Quick question, what is the time constant for the prediction? Is it a few seconds or?
That's a good question, because I didn't know. But yes, that's a challenge. Yes, this is offline computation. We need really make it real time. That's why I think your institute has amazing work.
So prediction means can you predict this frame 3 seconds before or 10 seconds before?
I see. Okay. It depends on the configuration, but I don't think that it can go over 1 minute or 2 minutes.
Yes. 1 minute is a lot.
Yeah, 1 minute is a lot because we need a bunch of data, but depends on the size of the network. But right now, like Sora from OpenAI, it's also 2 minutes, 3 minutes. I think it's go over 1 minute. Some context is not going to, doesn't make sense. So 1 minute, I think it's the upper bound right now if we have a big network. But it's a trade-off with the computation overhead. So for this particular setup, sorry, I don't know what the size of the prediction is. Yes, so we need more data. It's a chicken and egg. Once we have this world simulator, then you can get the data from the simulator. But in order to build this world simulator, you need the real data first. So we are collecting data from all over the world. Idea is simple, just distribute the cameras, LiDARs, and our partners around countries, they give us data. We really need to address each region regulation because data is, is an IP, sometimes has some regulation to go across the countries. Yeah, we can somehow address it in the future. Also, there are some details. In order to do this, we couldn't find any, optimized cameras from the market, so we developed the new camera. Most of the cameras are not optimized for autonomous driving, so we developed a new one with our own design because we understand the software requirement. We can highly tune up the camera parameters module in order to work for AutoWare. So now most of AutoWare users are using this camera because it is functional, in many conditions. And yes, we have fleet management applications because the whole experiments, we need to collect data. Sometimes, yes, the fleet management is not only generating routes, but also collecting some errors or incidents or some failures in the system, so that our developers always look into this analysis and reflect it onto development. So it's going to be development operations tightly coupled. The DevOps framework is very important for us to make this engineering. And as I said, yes, Japan has many now projects going forward with level 4 deployment. So we really want to make model case in Japan and expand it for international countries. So yes, DevOps is very important, like run to run. It's a cycle, always chicken and egg. So we provide this DevOps environment, and sometimes the stakeholder often ask me, hey, did you give up research? No. I still do computer science research. My major is operating system and computer science. So we're building real-time, low latency, high quality operating system and system software using some, say, state-of-the-art from academia. Also, we're building LSI, SOC, application specific. This is my original PhD topic, is the building SOC. So we optimizing software and create a logic, low power for running auto-ware in real time. So I almost conclude. So we have basically tried to build the full stack, but unlike other companies, we want to make it open. So if you look at the entire stack, right bottom, all the way is open source. So source code is available. And other features like design, architecture, it's not source code, but it's still open. So you can look at the design or architecture for you to replicate, modify what we are doing. Fleet management or cloud system is also open in the sense that we have API interfaces so that third-party fleet management systems can be easily connected. So in Japan, we working with rideshare application, which is not provided from our end. We only provide base fleet management connected to autonomous vehicles. But from users' perspective, they don't want to use new rideshare application. So we have interfaces to be connected to the existing rideshare application. That being said, I don't think that we can do everything by ourselves. So this is a little bit busy picture, but you can imagine that left, small computation power use case, right? High performance computation use case, like robotaxi. Low computation power use case, I think we can do alone, like factory automation, AC. But once you step into high performance computation use cases like robotaxi, passenger car, there are some cutting edge players like Waymo, Tesla. The black circles, you can imagine that Waymo, Tesla. We thank them because they showcase the cutting edge, so that if we collect right partners, AI companies or top universities like CMU, I think that because we have the baseline, we only need cutting edge AI algorithms or war simulators so that we can reach the cutting edge without spending tremendous capital injection. Waymo, Tesla, it's 20, 30 billion dollars investment, which is not sustainable. We believe that we can provide this with open source software as a basis. As a matter of fact, Waymo can only do robotaxi, from my point of view, but we can do everything else and all types of applications. So if you compare capital injection and achievement output, I believe that the open source software is much more powerful, efficient, and sustainable, so that we are trying to build this ecosystem, taking some time. Okay, I can stop here and switch to the full to follow up what we're doing. Thank you very much.
All right, it's a great pleasure to be here. This is actually my 25th year reunion weekend also. So as you can see in my card, I was in CMU for bachelor's for 2000, in 2000, master's in 2002, and then in 2008 I got my PhD. And I went to University of Pennsylvania after that. Thanks to Raj, Professor Kumar, for a lot of mentorship over the years. So over the years, starting from real-time systems, embedded systems, a lot of my research has migrated to this intersection where we work on life-critical systems and essentially applying, formal methods, so abstract and logical mathematical models to capture complex interactions between systems and controllers, but to ensure safety and guarantees for a variety of safety critical systems. We apply that to controls, and we have a lot of machine learning under the hood, not applied, but in capturing the dynamics of the systems. And so over the years, we focused a lot on medical devices. So this is implantable devices like pacemakers, defibrillators, cardiac modeling. Currently, we work on physics-informed neural networks for capturing the dynamics with the heart to generate patient-specific models in real time for surgical guidance systems. We work a lot on energy systems. We had some spin-off ventures from that too. But obviously today I'm going to talk about not so much my research per se, what we do, but really what we do together with Shinpei, with the AutoWare community. So this is a little bit more on the applied side, not on the so much on the theory aspects. Generally, the theme is that we are broadly from the academic side. We look at the work we do with AutoWare as AI agents in the physical world. So it's much more abstracted out, but it's also very applied. You will see, and so as mentioned before, I wear a couple of different hats, but two of them are related to AutoWare, where I just stepped down from the board last week, and then I also direct the AutoWare Center of Excellence. This is actually, we call it centers of excellence because there are over 32 universities that are part of this. They all have AutoWare-enabled vehicles. They all do research on AutoWare. And that's a really great community. And then we also have these small-scale vehicles and classes that are taught in CMU now, and with the F110 and Robo Racer. So as Shinpei mentioned, AutoWare so far has tasted success with robo-taxis and buses in Michigan, fast cars, a lot of logistics-based vehicles that are in these kind of closed systems. And this is all made possible with these 80+ partners that are academic institutions, but mostly industry partners that contribute directly to AutoWare. So I'll talk about some of the themes where we are going in over just the next year with that, right? So this is not necessarily like a giant roadmap, but so the first theme is really in software-defined mobility. As we come to these kind of skateboard EV chassis, this basically makes software such a first-class citizen because the rest of the platform is becoming more and more commoditized compared to vehicles today. So we actually are, and this is also in collaboration with several CMU faculty on looking at software-defined manufacturing, software-defined design of the vehicles, sensing with Swarun, and then testing actually. And so the big sort of change over here is that now, you can do this on demand. You're designing the vehicle, you're basically configuring it, you're customizing it, and because it's become so modular and so sort of much easier to integrate than say like, if you're building a Toyota Camry, you have to make at least 8 to 10 million units to really break even. Versus in this case, now you have these very configurable chassis. So going from an ICE internal combustion engine with over 2,000 plus components, this reduces down to less than 20 modules. And there's no even a need for an axle because each of the corners have their own suspension, powertrain, and control system. And then they just expose this sort of API essentially after this point. And these manufacturers are also kind of generic van manufacturers with these kind of white label manufacturers. And so this is really going to really hit a lot of the incumbent US automakers pretty hard as we go here. But we are not competing with on-road systems over here. We're really looking at, well, instead of making 8 million vehicles, they can never make like say 35 to 250K vehicles for say ag or for mining or for some kind of last mile use cases or for logistics. So this is an approach where we can do that. The other big change is that the number of electronic controller units is going down also an order of magnitude from almost 100 to just about 3 main computers that then operate on these. So the architecturally also, these are getting more simplified in number of units, but more complex with the cross-platform interactions over there. So our goal over here is that to work with these electric vehicle platforms, so to have open autonomous vehicle software with AutoWare on open standard electric vehicles, where standard means commodification and then configuration with that. But for a lot of these off-street use cases, right? So for mining, logistics, and that's where we are working with different partners around in the industry with academics and at that intersection where you can have your skateboard platform and then just configure it for a minibus, for a sedan, for a mini truck, and so on in a small scale manufacturing facility, say about 10 to 20,000 square foot. And you're able to now roll out, on the order of about, 60 to 80 units a day. So again, it's really making this more of a micro manufacturing view, where now you can have these systems at 80% modular, 15% configured, and then 5% customized. And that allows it to operate in this kind of new mode of manufacturing. So to do that, we started small, right? I mean, we have our lab. So just like y'all have Mill 19, about 12 years ago, Penn got this 23-acre facility outside, just next to our campus. So that was quite remarkable in Philadelphia. And we have these garage labs, and that's where our AutoWare lab is. We build electric vehicles and autonomous vehicles in and out. And this actually has none of my PhD students. They're all master's students. All the PhD students do the theory stuff, and then these guys build. But they are so self-organized, and they just are so motivated and driven. And I'll show you some of the projects. So they're much more hands-on. So the first theme that we will get into is software-defined manufacturing and integration. And how do we actually, go from generative design or AI code designers for doing design auto-completion. So where you don't have to start from scratch, you have sort of seed designs, and then you mine them in a knowledge graph, and then you use that to generate new designs for new requirements with doing architectural exploration, parametric optimization, and then generating these new designs. So kind of like Jarvis with Iron Man. I had a better slide than this, but that's sort of this, approach for systemic generative design that we will use as to sort of cooperate with the whole CAD pipeline, right? The testing is also over here. We have virtual testing. You put the vehicle on a dynamo, and then you can test this out. This is with our partners in Clemson University to then actually have this virtual testing. So as you're rolling it out, even though it's in about a 20,000 square foot facility, the last sort of facility, kind of like a car wash where they're drying you at the end, they're testing the system out, but in this virtual sort of environment. And then this has a lot of this testing capability to basically go through subsystem by subsystem and interact with the vehicle through that, right? Without it actually, before it even gets on the road. A lot of the partners actually who work with AutoWare, they develop these kind of chassis. This is just one, there are several of them. Picks moving, and they have configurable ones. This is just for research. This is actually just for universities, and many of the university partners have this chassis. They bring it to our conferences for ICRA, IROS, wherever we go. And now this is in production. There are many of these design concepts, but they actually, this is real. It's not an AI image. So, and so with that, we basically are working to build this sort of stack of software-defined future mobility and work towards that. And then these are this is the actual platform I showed you there, and then other sort of smaller scale vehicles. And the nice part of that facility, like our version of Mill 19, is that all the partners keep coming and going, and they work together with the students and the many different professors from Japan, from Michigan, Delaware, and so on. So a way to bring in this cooperation was really to bring in academics to be first-class citizens as part of AutoWare, as users, as contributors, was by setting up this AutoWare Center of Excellence about 2 years ago. And now we have over 33 different universities. All of them have vehicles, all of them have this expertise. And so, like say, for example, this Zednek from Czech Technical University, he spent about 8 years of his life setting up the model-based design in Porsche in Prague. And that's a 350 unit, 350 person department for Porsche just on software. And so each one has this expertise and they are all sort of very involved. And we have AutoWare sort of specific projects with them. That, right? So from computer vision to full stack to connected vehicles. And I won't put these guys as some, fluffy systems guys. I think that used to be the trend in the 90s, but where systems but they are going quite deep into actually construct not just applications, but building their system, right? So integration of LLMs and VLMs with AutoWare is another emerging theme with Purdue. So the next theme is really like, okay, where else, where do we go beyond? So one of the directions also where we're working on is going to off-road and space. And so we have these current, driving scenarios. And now there is a lot of interest, say, even from the Japanese Space Agency, to actually have these vehicles that are much more like you can design them much faster in a much more competent manner for missions, because there will be many more missions happening. So one of the sort of thrust that we've started on is to design the vehicles with full dynamics, the terrains, and to have these. And to kickstart that, our team participated in these NASA competitions. They got 3rd place in the first one they went for. This was on the Mars challenge, and then there's the 2nd place in the next one for then the Moon challenge, right? And so to do that, you have to build a lot of these building blocks, and that's where we wanted to start up with, and building that system over here for making sure that when we start to have AutoWare running on these vehicles, they still have a similar stack, but they are very optimized for the computation constraints and for the environments, and being able to have essentially learning-based perception, planning, learning-based control, where you're doing a lot of adaptation online. So, because you're not going to be able to really capture those environments fully, right? So that went through a lot of the sort of the design for those parts, and now it's really building these kind of vehicles and going in that direction. So the other sort of theme is really on looking at is building reference platforms. What can researchers use that actually run AutoWare? And so we have our small scale vehicles our mid-scale vehicles. And these are all sort of student built, but everything is open source. And then the same design gets replicated in Hungary, in Poland, in Korea, in South Carolina. And so that's the way we can share these, but they're all like sort of running AutoWare. This also says you can start cheap and small, then you can start growing with better, higher fidelity dynamics, better sensors, and so on, right? So as you sort of scale up to real world systems, so that is kind of like an on-ramp as we go through that. This is just one project we did. Now it was just really to have the students in the master's lab do the full stack, go from mechanical, electrical, power systems, embedded control, full autonomy stack, all in 4.5 months to build the system. The only thing we got off the shelf was this blue frame. Everything, and of course a seat, but everything else was machined. And but that was like a 6-person team to begin with, and very dynamic, and probably 200 different problems to fix. And then they have this full drive-by-wire system with with a digital twin, and this is sort of like testing in our garage facility over there. And this was when we just were starting up these platforms, right? And everything is fully documented, open sourced, and that's how we share the designs of that, right? So, and to do that, we also have digital twins. So this is our real campus. This is a twin campus, and then testing out the vehicles. And it's very easy to use, but they have like very high fidelity interactions with the environment. And but it's running the whole stack over there, right? That's the main thing. It has to be useful, not pretty, just pretty. And this was generations of the teams, and then they go on to have really good jobs afterwards, and they're all very successful moving on from this. They won the 2023 competition. That's one team. And then there was a competition with UC San Diego, Purdue, Berkeley, and then our team won again in 24. We won't race in 25 because we're able to do that now. And so that's just showing, okay, how to build an AutoWare-enabled platform and get it to race and drive in this 4.5 to 5 months time frame. So 0 to hero kind of thing. And that gives a lot of confidence to the team also as it goes through. So same thing is replicated in factories in Korea now and going on. We had CMU faculty come and visit us and see our labs at Penn. And then it's also sort of like a lot of the use of AutoWare in our 23-acre facility is really to have navigation basically within 1 hour. That's what we want to do. Autonomy at a basic level with behavioral planning, with the maps, everything, all to operate in a out of the box. Right? So, and then we also have built these off-road racing vehicles that are now working with multi-terrain interactions. And that's sort of so that with education outreach, our goal is, of course, to show the full stack and how to expose that to students over here. We built these cars. This is just the first generation. It used to be called F110th. Now it's called Robo Racer because it goes to multiple scales. But it's also, that time it's 1/10 the size, but 10 times the fun. And now this is it has very good simulation environments to build your stack, test it out, and then deploy it. And the good thing is that we help the community with building, coding, racing. And it runs SLAM on board. It's running RRT, all modern planners on board. And then it's running model predictive control, MPPI, everything on board. It's all part of the standard stack. And we have this course. It has been taught in at least 36 universities now. And there are no exams in the course. They're just races, actually. Race 1, race 2, race 3. It's very, very fun, very challenging. Our whole goal is to go from concept to code to competition and to get the student to go through that pipeline and have a great time, but it's very challenging also. And they do many different projects on perception planning control. We just kicked off our projects. I was in West Virginia University yesterday. They have a whole class. John Dolan has a class here. Dozens of US universities, TU Munich, and so on. And so let me see if the audio works here. But so this is just showing like what is happening under the hood, right? So this
you collect lots of data. You can use ROSBAG to collect data and use Foxglove Studio to visualize it. Let me show you.
So this is just showing you what's happening under the.
Right now is the Cassiopeia, the associated ROSBAG being played back in Foxglove. The LiDAR point of view helps us understand how well the car is tracking the optimal race line. The speed graph helps us understand throttle control and brake timing during a lap. We also measure accelerations to estimate the car's available grip budget. To debug our obstacle avoidance system, we plug out the laser range in front of the car.
So, and then with that, we had many generations of students who passed through. So this was actually one of the first students. He was the head of motion planning in Tesla for about 6 years. Then last fall, he left to start bot company with Kyle Vogt from Cruise. Their first round was, I think, 150 million. But the point is that they can realize their dreams, and they are really good enough. And many became professors. This is just from the early days. It obviously goes down till 25. And there are over 90 universities that use F110 Robo Racer now worldwide, and they compete. And we also have many workshops with this, and they're very well attended. And then we have theory workshops. Right? There's no systems people, just math over here on multi-agent dynamic games, and looking at like from economic theory to really mean field games. Working within, but with full dynamics and continuous motion. So, and then we have a lot of competitions. This is in ICRA, just after COVID. They all have the same platform, but it's a battle of algorithms. And last year we had 9 competitions worldwide in all these different places. And we'll have one in ICRA again in May. We'll have a joint competition with CMU, Lehigh, and some regional folks also just for fun here. They all build a map, they find the racing line, then have to come up with overtaking strategies and work with that. And so these are very exciting teams. And this was in Korea just last, and they're always part of some transportation, robotics, or controls conferences, right? So I'll just spend maybe 3 more minutes on what research we do to power a lot of stuff in the upcoming stacks for outerwear. So normally people in civilian driving, like say this car is trying to merge, is not being able to get a place in. But for us, we can nudge through and get across. But for autonomous vehicles, they really struggle with non-cooperation. And over here in the civilian case, obviously there are so many different evaluations you have to do to forget about certification. Also, just even testing is so large. Verification is not even part of a discussion, for a real discussion. But here you're just optimizing safety. Maximize safety. If I reach home 2-3 minutes late, no big deal. It could be the traffic, it could be something else. No, but that didn't give us a good problem. It was too open-ended, vague. So we said, let's focus on racing, where we have this tension between safety and performance. And so with racing, you get penalized for being overly aggressive, you crash, you're out of the race, or you get penalized if you're too conservative. In fact, if you're only half a second too slow in your lap time, you're out of the top 10, boom, that's end of career. But it's not all about speed, right? So 40%, only 40% of the racers who won actually had the fastest lap time. 60% of them just really good at balancing aggressiveness and restraint over there, right? And that's what we are trying to achieve here. But you're operating with full physics, full dynamics, high speeds, high accelerations, fast reaction time. You have to be operating at the nonlinear limit of your tires, of your engine. If you aren't, you're going to get outcompeted over there. So you have to understand how to capture those in your. Crashing is expensive and dangerous. Sensors, radars, all the stuff you see off-the-shelf stuff, They only tell you what's the pose of the other agent, what's the short-term prediction. They don't tell you what's in the mind of the other driver. And that's what we want to know. We want to know their policy. We want to know their intention. And that's was part of some of our work in really doing, capturing, policy estimation. And secrets, strategies are secret. It's not like I can go back to 1955, mine all the races. Every race is different, vehicles are different, driver's mindset is different, track conditions are different. It's a small data regime. So our theme is how to get safety through agility. And so I'm just not going to go through the research fully. I'm just going to give you like 6 more slides and we'll finish up. So the first theme was how do we generate the most competitive agents that balance safety and assertiveness. And we had this in ICML, and we call it Formula Zero, because Formula One, the other set of rules. Formula Zero means that I don't know anything about my opponent. But through offline, I can generate a population of, say, 20 or 100 competent policies, which are very diverse. And then online, with the multi-arm bandit approach, we can actually now figure out what kind of mix of these offline policies the opponent is. And we can then predict how well they operate, what they're going to do next, what is their policy. And then we can outcompete them through that, right? And all the theory we do, we have like this is running on the vehicles, it's not running on an external computer, and we can show that we can do this online with just about 400 to 600 observations running at 10 Hertz. So very efficiently capture the, other things are, getting more formal rules for safety. How do we formally capture safety, but we don't want to be too conservative always. So how do we make adaptive safety? And so this was on looking at control barrier functions and how to learn how to change the parameters of the control barrier functions so that you can decide when to basically follow, when to sort of overtake, and it scales and generalizes really well, across tracks, vehicle speeds, number of vehicles. So it's really figuring out when to be conservative, when to overtake, and how to do that. And a lot of other techniques we use are with like learning control barrier functions, conformal prediction with more statistical guarantees, physics-informed machine learning. I'll skip over that, but that's just some. And then the other themes are like on, okay, how do you design the most efficient racers and automatically tune, but across multiple domains? So do super optimization across mechanical, control, and decision making. This was some work in ICRA called Tuner Car. And here we could actually automatically take any vehicle on this track and figure out how to race. Normally, a racer would follow this dotted line, brake, 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 and then speed up. And here our vehicle would push through the limits and actually come in really hot, drift, 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 drift across. And you can see the z-axis as the wheel slip, and then get out really aggressively. And then that's, so again, everything we do in code and simulation, then it works on the real vehicle. And then just to wrap up, there are also projects on like perception, learning-based perception, where we use invertible neural networks because localization is an inverse problem. And so with normalizing flows, we can do implicit map representation and then capture and do localization at very, very high fidelity and very high frequencies, consuming just a little bit of the CPU. And then this is just showing how we can, this is not real images, these are all generated images from this invertible neural network, and for that. And then also multi-friction, multi-terrain driving, and being able to use, like say, whether it's the Gaussian processes for adapting MPC or MPPI and so on, right? So I was just giving you a couple of snapshots of what we do, but our main goal with AutoWare is to make this a very active, community that can take all this real research that we do and put it in these platforms. But we take out all the issues that academics don't want to deal with the platform. Academics don't want to deal with implementation. We just want to see our research get into action. And that's what we are enabling over here. So I'll stop here. Thank you.
Questions?
When is the first autonomous F1 vehicle going to be allowed?
We have. for last 4 years.
No guarantee, but my plan is to set up in 2030 Riyadh Expo. So this year we have Expo in Osaka, and 5 years later we actually deliver a new concept in Riyadh. And Riyadh recently also invited the real F1 entertainment. So the government is now very much interested in making F1 by AI. So
Both using humans and AI. Right? That's great.
that's open question, but both interesting, like robot racing. And yes, I'm personally big fan of Formula One, so I want to beat the Verstappen by AI. But yes, timeline, 5 years is quite feasible, doable from both technology and social acceptance point of view.
Yeah, but the Indy Autonomous Challenge, they are already doing that, and actually many of our my former students from they're in TU Munich, they won the competition last year. From Mother Bell, my former PhD student, and UVA, he won. He's the fastest US team that right. So, but I think getting AutoWare into that is one of the tracks because it's highly specialized, but it is also much more narrow than driving.
That's a good point actually, because program setting is also very interesting. Like I explained, generative AI is becoming more and more beyond language, word models, including real physics. Racing may be very interesting use case for research evaluation, how you can imitate the real world, including not only textures but structures, but also physics. So if we can do racing, then I think we can apply the same technology to other use cases. So I'm from computer science. The whole technology is actually starts from supercomputer. So Formula One may be something like supercomputer. If we deploy the technology there, it can be used for other use cases.
Yeah, because you can make mechanical systems far more safer, right? If you know how to drive really fast and turn when there is rain and sleet and other things, that can save a lot of people in the real world when you actually spin out of control, right?
So, question for you, Rahul. You work on safe autonomy. You think AI is the way to go for safety, or AI needs to be augmented?
So so I think as just following up what Srini said also, like when you are working in these environments, that are dynamic, that means your frictions and your terrain is changing, then we cannot use a very explicit and deterministic, perception planning control, kind of like what we have right now with AutoWare as that pipeline. We have to have, a much more data-driven, feedback-based, where your controllers and your planners are tuning on the fly. But then using, I think the current approaches like, these safety shields, control barrier functions, conformal prediction, physics-informed neural networks, I think they're providing us a start. They are not yet like, I would say strong enough in terms of providing our safety guarantees, right? So they build in some robustness in the system, and not all of them provide any guarantees. They provide a statistical guarantee, which from a real-time perspective, we don't particularly like. So I think, we have to build in those techniques. There is obviously this very modular approach of explicit, I'll just call it explicit versus end-to-end. But then in the middle is really like where you have like a differential stack. You're communicating the gradients from perception to planning to control. So the uncertainty propagation is also very well estimated through that. And I think that's one approach to achieve that.
Thank you. So Shinpei, I think it'd be useful for this group here to know, I guess, about what deployments you have with AutoWare in Japan, and then what your vehicles are capable of. They can drive 15 miles to the intervention, 1,000 miles with the intervention, things of that nature, practical, empirical experience that you currently have in miles. So I think this would be
The performance indicator by miles per disengagement setting.
correct.
Miles per disengagement really depends on dynamic. If there is highway, then you go for straight line. This is. So I would say so. So level 4 certificate in Japan should never allow human to basically intervene. So you have to. That's why testing or verification, validation, very expensive to showcase that under the given OOD design domain, like route, weather condition, you have to show, prove by somewhere, somehow, the vehicles do not need any human interaction. So that's autonomy 1.0. Autonomy 2.0 is to increase the size of this design domain, like what Tesla is. So Waymo is 1.0 because it's limited area, limited condition, but they also guarantee some level 4 certificate. Autonomy 2.0 is like Tesla. It's improving the size of area or design domain at the expense of the level of how to say determinism. So Tesla is not level 4. So what we have to go for is autonomy 3.0 is combinations of maybe Waymo and Tesla with open source due to some cost reduction, increasing the size of design domain, at the same time still guarantee the level of to level 4. But that's open problem. But in Japan, yes, if it's limited condition, we can actually provide no human.
So in your view, we are 1 year away from that, 5 years away from that, 10 years from
Autonomy 3.0, maybe 5 years.
Any other questions, comments?
I'm just curious, you were mentioning in addressing this sort of tension between performance and conservative or safety.
Safety performance.
I understand the advantages of the data-driven kinds of models, but how do you protect against the mistakes that it makes, or I'm thinking of the LLMs, for example, where they do amazing things, but you can also get in a lot of trouble if you just follow their advice.
Yeah, number one, don't use LLMs for AVs, but not, unless.
Right. But I mean, do you find the same kind of circumstances where one
Definitely.
trade-off of robustness is you're not really certain what's going to happen?
Yeah, I'll let Shinpei address that.
Well, that's open problem, definitely. But the concept, I think, is going to be a redundant architecture like this. So disk is a array, is a combination of multiple disks to make it extremely low use cases for failure. So if that's why I think the collaboration between machine learning people, computer science people, and engineering people to develop a right redundant architecture, a single failure point should not influence the system safety. I think which is an expectation for the line of work, but I think it's
Yeah, no, I
all
can see how that could mitigate some of it. It just seems like, at least my understanding of listening to some of the autonomous driving, is that there's such a long tail of special cases that I don't know. It seems like you're always kind of trying to beat down the last one.
Yeah, and those are also rare cases. So you have,
Yeah,
so, I mean, the question is, what's a search engine to find these, an efficient search engine to find these, rare incidences or these rare accidents. That's why we focused, at least from the academic side, we changed from our work with, say, when we were doing Mobility 21 was on what's a driver's license test for driverless vehicles to something a little bit more constrained. So say, okay, can we at least, really, do very well and provide guarantees in this constraint, and at least solve that within the, say, racing constraint or within logistics or these off-street use cases on the practical side. And then we can grow the bubble, because from Shinpei's side, he's rolling out, he's working in the real world, he has to actually engage, with wherever demand is there. But from the academic side, we have to answer this safety question every day.
Yeah.
And so we're saying, okay, well, what is the biggest bubble in this, or the sphere of, this very high dimensional operational space? So how many dimensions can we go up to and still provide either a hard guarantee, statistical guarantee? And we are not in the, complete drive around in the wild setting.
Yeah. Fascinating stuff, yeah.
Hi, thank you, Shinpei and Rahul, for sharing your work. And to all today's attendees, thank you for your questions and for joining us. Today's presentation will be posted on the Safety 21 website, What's Happening page, along with a link to the video of the presentation. For students who are interested in engaging in transportation topics, the Transportation Club on campus is a great way to plug into transportation topics with fellow transportation enthusiasts, a lot of transportation in a sense. Thank you for attending our Smart Safety Connection seminar. We hope you'll be able to join us again for our next session on Friday, April 11. In the meantime, please feel free to contact us with any questions. Thank you.